Okay, this is our final project progress report for our final project. We're team four. So the first thing we had to do so far was configure Kyle for accepting the new board that we're using for this project. So the first thing we had to do was install the board in the pack manager. You can see circled in the red square, right? The first pack was the board itself that we had to download. And then we had to download the STM32U5 support, but not the latest version because that didn't support the header file. So we had to download a previous version of that for our thing to work properly. Then after making a project, you just have to change the target options for it. The first one is changing the software model to trust zone disabled. Um, I couldn't figure out how to get the trust zone to work, so by just setting it to disabled, that allowed our code to be able to compile. The next thing was changing the debug settings. We had to change that to the ST-Link debugger. The one it was set to by default doesn't recognize the board, so we use the ST-Link one. And finally, we had to change the scatter file and the linker options to the one circled in the red here to that. Otherwise, you get errors when building the project. And by doing all that, that allowed us to start working on the project.
Next, the first project we tackled was the ultrasonic distant measurement system. First, we want to find pins that would work with our setup. So we need two pins, a trigger, and an echo. For this, we chose the GPIO pins on CN3, which is the STMod +1, and we chose PE4 and PF5. However, for echo, we need a timer to be able to time the distance between the echo start and echo end. So we made sure to choose a pin that has a timer that would be easy to use. In this case, we could see PE4 as a timer 3, channel 2, in the ultrastrip function 2, which we use later in the code. The main protocol that we're going to be using is the IRQ protocol. So we use the IRQ handler of timer 3 to handle all the echo start and end. So first, the function does it when it's first flagged for the call, and on CC2, it'll detect the start of an echo pulse. So that's like the if edge flag equals 0 as before the echo is started. So then we set the CCR2 to whatever it was when it was first captured, and then turn the edge flag on. Therefore, when we exit this IRQ handler, when it's re-triggered, when the timer's re-triggered, it'll then go to the edge flag and else case. As you can see, when echo starts, it's falling and counting down the time it takes to reach the end. And then once it's re-triggered, in the else statement, we capture the echo edge after it was on the falling. It was capturing that falling edge of the signal. And then we're ready to capture the start signal, the rising edge again. And then once we have an echo end, we're allowed to do the bottom function to get our echo duration, which is the echo end minus echo start. And then we also utilized a simple overflow statement at the bottom, just in case the start was greater than the end. And this is the output that you see, where the number outputted is just a simple centimeter approximation of what the sensor sees, be it a wall or an object. And it can change about every 100,000 milliseconds.
Right, so the next part after that we had to figure out once the sensor was working was how to actually look at the information, and we went with looking at it on a serial monitor communicating to the computer over UART. So to communicate to the computer over UART, we had to use the virtual ST-Link COM, and if you look on the left, the part circled in the red, we see that UART1 is the UART channel that's connected to the ST-Link, so that's the one we had to use. And then going to the table on the right, we can see that pins A9 and A10 on alternate function 7 are the pins used for UART TX and RX. So those are the pins that we have to enable for communication to happen. So I made this little C file here, UART utils, which handles all of the initialization and methods needed for our UART communication. Starting with the UART init file where we enable the clocks for both the GPIO pins that we need and also for the UART. And after that, it's just the same as what we did in class for the transmit character method. But I had to add a few new methods, such as the first one was the transmit string. So this allows us to just put in multiple characters instead of needing to use multiple statements over and over and over again to transmit uh, longer information than just a character. And then from there, I was able to use that to make the transmit integer method, which I can put in an integer value, like a value passed from the sensor that gives us the distance as an integer. From there, then this method just makes it as easy as passing the value of that variable into here to convert that to um, a string that then can be sent as characters over UART, right? And then on the right, there's the int to string method, right? This is how we convert that integer value into a string, so then it can be passed to UART string. And then I just made a header file for it too, right? Because we figured we're gonna want to be able to use UART for both of our projects, and by just organizing it into its own two files that we can just import in either project would make it nice and easy to implement this for both the ultrasonic sensor project and the IoT project. So this just made it simple to do that.
So from there, when we finished our ultrasonic sensor, some improvements that we could make in the future, going to the end of the project, was make it more accurate by implementing float values. As you can see with our UART, we implemented a way to send integers, strings, and characters. We didn't quite get to making a function like UART that would trigger the float values. So that would be the main way to overcome this problem. In the ultrasonic sensor file itself would be pretty simple. Just change the distance from an int to a float, but setting that value is where the problem could arise. Uh, Further modifications we do is the distance function itself, because the echo duration comes as a raw value based on voltage that doesn't really um, give like an exact measurement. So fine-tuning that function to give like exact centimeter or meter measurements would be ideal. Uh, Another one is testing the delays, where currently we're utilizing like a specialized DWT function, while it might be more simpler to use another like simple timer with a count in order to implement delays between trigger pulses. Finally, I want to improve testing of the echo duration overflow, because right now the that else function in the IRQ isn't activated very often, and it seems to perhaps not be working as intended when an object is very close, where it's reading out a bigger value than what we want.
All right, next was on the IoT project. So for the IoT project, we're going to use the HTSS221 humidity and temperature sensor as our like input data from the board. And from the data sheet, we found in this top left that to communicate with the sensor, we have to do it over I2C. And the one that we're using is I2C2, which has pins H4 and H5 as the ones connected to it. And if you look in the other table, we found that pins H4 and pin H5 is connected to I2C2 on its alternate function 4. So we know that when we set it up, we need to set those pins to alternate function 4. And so the first thing we did was just our initialization of the I2C, where we first enable pin H4 and pin H5 to alternate function mode 4 so they can communicate. And then the next part was enabling the I2C2 part. I'm not fully sure on how all of this works. I used a lot of assistance from ChatGPT to get this working, and I need to do more research on what everything is exactly doing. But right now we have it where it enables the I2C2 to enables the channel and gets the clock frequency to 100 kilohertz for communication, which is the slow mode, which is supported by our sensor. And now the other method we have implemented is the I2C2 read HTS221, where what this does is it just reads whatever is stored in the register address, and it copies um, what's stored at that register address on the whatever you're communicating with to the data parameter. And then the length is just the expected length of the data. Um, so I'm not really entirely sure what's going on with this either. Right, I used ChatGPT to help me come up with this part by passing it information on the board and the sensor. But I know it works because we did some testing. The way we verified it was using the Who Am I register on the sensor. Right, at register address 0F, the sensor stores its Who Am I value, which is BC in hexadecimal. So by just using the read HTS221 at F and storing the value, we see that we printed out the value after reading the register to our serial monitor using UART, and it printed out the value 188, which in hexadecimal is BC. And by going back to our original table, we see that the who am I value of the sensor is BC. So that lets us know that we did establish communication between our board and the sensor. And so now all that's left to do for this project is creating a I2C2 write HTS221 method so that we can write to the sensor. We need to be able to write to the sensor just specifically to be able to turn it on. So then it'll start recording values that we can read later. And then we just need to finish the other parts of the IoT project also, like enabling the Wi-Fi on the board so that we're able to communicate with an online cloud platform like MathWorks ThinkSpeak, which is the other thing we need to do in order to start collecting data. And that's the progress we've made on our final project so far.